Okay, we are on this page, right? Next step, we are going to find out the film shape. Okay, we want to know about the film shape. Film shape, it curves, right? And we have already discussed about x. X is the same. X is not a function of location. And for moving coordinate system, x is not a function of time because for the moving coordinate system, everything is steady state, right? It becomes steady state. So x is constant. Okay, HLTB is highest over here, right? HLTB is highest over here. And HLTB is lowest maybe over here, correct? So when HLTB is highest, VF is lowest. So this means over here, VF is lowest and VF become higher, 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 higher. The reason of that is we need to have mass balance. Okay, mass balance should happen. So mass balance means what for the moving coordinate system, whatever go through this boundary should go through this boundary too. Okay, so this is why it is become faster and faster and faster. And in fact, we have basically this equation is x equal to delta v, which is VF, multiplied by rho A H L T B, right? So what is that telling me? It tells me that x, which is the shedding rate is constant. Okay, so when HLTB go up, relative velocity go down. When HLTB go down, relative velocity go up. When we have that, then we have constant shedding and pickup rate. Make sense? So let's take a look at equation for x one more time. See this x? X is, okay, let's change the laser pointer. X is relative velocity, or x, first of all, x is constant, right? So when we look in the film part, for the film part, we have VF, which is this term, multiplied by HLTB, A and rho. So x is constant, this means when HLTB go down, the relative velocity go up. And the reason of that is so that the pickup rate is the same. So we have fluid go to the next slot for pickup. So if we have too high relative velocity in this part, okay, too high relative velocity. So let's say this part, the relative velocity is too high. What happens is liquid mass that go to the slug front over here. So liquid mass that go to the slug front over here is too much. So that's too much to pick up. So when it's pick up too much, the slug body length expand. It's not at like steady state. So the trick here is they assume steady state. Steady state means nothing change with time. So for the moving coordinate, everything is steady state. So the rate of pickup has to be the same rate of shedding. And mass, that for the moving coordinate system, everything inside the liquid film move backward, right? So when it move backward, it has to move backward such the way that the pickup on the next log is the same as the shading from the slug before it. So slug 1 shed some mass, next slug should pick up the same amount, not pick up too much or too less. Okay? So when we have steady state in the moving coordinate system, we cannot have steady state, right? But for the moving coordinate system, they will see it as steady state. Nothing changes time for moving observer. So because we want to have steady state, x has to stay the same and vf has to change along the direction. The relative velocity has to change so that x remain constant. Make sense? Okay. Alright, now we want to get a fin shape. To get a fin shape, we use the same trick. Okay, use some kind of force balance. So we know that force is the change of the momentum per unit time, dmv by dt. So we have v dm dt plus m dv dt. Okay, that is force. So I put here that in the translational velocity coordinate, the velocity is not a function of time, but only a function of position. Make sense? Moving observer will see the velocity at that location to be the same every time. Okay? Because everything is like frozen with respect to moving observer. Okay? So dF, what is this force? Okay, hydrodynamic. Okay. This force has to do with, force is, I put here, momentum. Okay, momentum multiplied by mass rate. I try to calculate dmv by dt. So AP multiplied by ρ, this one will be AL, right? Cross-section area that occupied by liquid. Cross-section area that occupied by liquid multiplied by relative velocity. So this one will give me kind of volumetric flow rate in the moving coordinate system. Okay, volumetric flow rate. So V times cross-section area is volume per unit time. Okay, volume per unit time multiplied by rho will be mass per unit time, m dot. And I say, okay, m dot multiplied by V is the same as dmv by dt. Okay, roughly that are the same. So instead of writing it this way, basically okay, let's clean the screen a little bit. We drop this term. Okay, we drop this term because dv by dt is 0. No change of velocity with time in the moving coordinate system. So we have only the first term. So it's a velocity multiplied by m dot. Velocity is this one, right? That's velocity. And the rest is m dot, mass per unit time. So differential infinitesimal change of force will be d of this whole thing. Basically it's a v multiplied by m dot. So that is df. Okay. So I put here summation of f equal to right hand side. That's everything. So we have df, we get df, right? df is the same as summation of df. This is left hand side is total, right hand side is summation of each term. So each term I have force number 1 is so shear stress, the unit of shear stress is tomitope. What is that?
Force per unit area.
Force per unit area. Very good. Yeah, it's force per unit area, right? And we multiply by unit area. So SF dz will be dA, right? Infinitesimal area. So this is a force due to friction tau F. Where is tau F? Tau F, we'll put it here. So it's a tau on the film part. On the wall of this film. That is tau F. Okay. SF is curved section, the part of the pipe that touch with liquid phase. Okay. So this is friction from the film, and we have plus G sine theta AP HLTB rho dz. Oh, why should it be plus? Let's go back. Typically it's kind of minus, right? Let's go back. What is plus? What is minus? Let's erase everything. So I put here this direction. This is also from the book, okay? This direction is plus z, positive z. So this time when we go to the left is positive z. So gravity term is this one, right? And theta is that. So G sine theta is that. And this time G sine theta is the same direction of z. So it is positive. Previously it's negative, right? But this on this coordinate system is negative. Okay? Write the picture correctly, okay? But if you get, yes?
So how is tau F different from tau WL?
It's the same. Tau WL is for the case of stratified flow. Tau F is a film in the, which is stratified flow, the film in the snug body. It's the same, kind of same. So if you didn't write the picture correctly, don't worry much about your quiz score. Okay, we dropped 2 lowest. Naturally, you fine?
Yeah, I'm fine.
Oh, okay, you're fine. All right, Raymond, yes. Yeah, that's what Shoham draw in his book. Yeah. X is that X. Okay, X is that X. Shedding rate. Shedding come from next line, right? So we have force is mass times gravity. G sine theta is acceleration, right? So this part has to be mass. Mass is area. This part is area, right? Area multiplied by dz is a d volume. Volume multiplied by density is kind of mass. Mass G sine theta, so this is a gravitational term. So the force that act on the film, we have friction, gravity. What about this? Minus d p bar AP HL TB. Does this thing make sense to you? Not very much? Oh, where's that from? Yahweh Cheng, okay, Yahweh Cheng, where's that from? D P bar AP HL TB. From the book, of course. Did you read the book? Jie Sheng, what do you think about the last term? Do we have it in the book? Where's the equation 3.102? Which page number? Don't know. I don't care. Doesn't matter. Which page number?
95.
95. Okay. At least you know the page number. And they have that kind of term, right? So the explanation is on the next page. Okay. Let's take a look at the explanation. Hydrodynamic of the film. You notice that hydrostatic head on different locations, they are not the same. Because the height is not the same. Different locations have different hydrostatic head, right? Okay. So dP bar. P bar is rho GH. Hydrostatic pressure. Okay. So at this point, let me clean everything. So potential, okay, at this point, hydrostatic pressure will be rho g h, and h is this h. So pressure at that point. Pressure at that point will also be rho, of course, g cosine theta and h, right? Pressure at that point. So average pressure will be, they use H1, H2, so H is kind of liquid height. So we have force in the direction of plus Z. Force in the direction of plus Z. That one. Oh, the other one, correct. I did it wrong. So force in the direction of plus Z is this one. So that is this pressure, P1 bar. Okay. P1 bar multiplied by cross-section area. Area. And force in the direction of minus P is that one, P2 bar. So dP is pressure at next location minus pressure at the current location divided by area. Okay? So it's a P2 minus P1 divided by area. And we know that in the positive Z, which is that direction, the net force will be minus dP. Okay, when we define dP like that. Alright, when we define dP like that, so the net force will be area multiplied by minus dP. So minus dP is P1 minus P2. P1, which is a taller side, minus P2. Okay, that is the net force. So because there's a difference in the hydrostatic head, so outside fluid push against the control volume from different sides. That force, they are not the same. Okay. So that minus dP, the area will be AP multiplied by HLTB. Okay, area multiplied by HLTB. So H2 and H1 here is like kind of may not be that correct. Okay, you may have to define H1, H2 like okay, H1 is half of this length, H2 is half of that length, or something, but it doesn't matter. In this derivation, it doesn't matter. So we have external force acted on the fluid element, which is outside push against the boundary. Okay, outside push against the boundary is minus P bar AP HRTB. We put it back. That is this term. Okay. All right. Good, right? So force that acted upon the fluid element equal to MA, or the momentum by dt, which is this term. Like summation of F equal to MA or something. So at this point, what we do next is take the derivative with respect to length. Okay, dz. So basically divided by dz on every term. Okay, mathematically it's not like that, but okay, engineering, we divided the whole equation by dz. So this term gone, this term will be divided by dz, right? Then we get equation 3.102. Good, right? So I put here that force is invariant in non-accelerating coordinate system. So force that experienced by observer 1 and observer 2, they are the same, provided that the frame of reference is not accelerating. So if I am rotating, there's an acceleration, right? Velocity is change the direction all the time. So the force will not be invariant. But if I move at constant speed, okay, have to sit on the ice skate and move constant speed. So force experienced by me from one observer and another observer, they're the same. So When we calculate F, we have to use the actual force direction. Actual force on stationary coordinate system will be tau F. Okay, let's take a look at this picture. Actual friction, liquid will flow this way, right? VLTB is that way. So tau F moving backward like that. Good. Tau F moving backward in stationary observer and also true in moving observer. So for this case, tau F is in the direction of plus Z. Okay. So if you want to know the film height, we do the force balance like that. So G sine theta is the gravitational force is in the positive Z direction or moving backward. Okay, so this equation is correct because not only is the same in the book, but I give you the explanation, right? Alright. So next we have to calculate what is P bar. Previously we have this P bar, right? And that P bar appear in this equation, that term, that's P bar. So next we have to check what is P bar. That's the next step. So P bar it is a pressure. Okay, pressure is the hydrostatic pressure. So I put here that P equal to rho G kind of H. Okay, but my H is kind of a little bit odd. Okay, it's not height, it's the how much liquid stay on top of that layer. So that will tell the hydrostatic head that press on top of it, right? So rho liquid density, G cosine theta is this direction, and H is how much liquid stay on top of it. The amount of liquid that stay on top of it will be film height minus the height of that location. So basically it is this one. Okay. So in your picture in the book, this front one is also from the book. So the amount of liquid that stay on top at that point is this layer. You see that layer? Good. So that layer is HF minus Y. Okay, that layer is HF minus Y.
Can you show in this picture?
That length.
Let's just verify. What is Y?
What is Y? Okay, Y is this one.
No.
Y is the coordinates, Cartesian coordinate system that we use to identify the location that we are calculating.
I know, but see, you have it on
That's
that.
Y is a vector measured from the bottom to the point where we do the calculation.
So we're not using the top of the field, so we're using like somewhere inside.
Start from the bottom. That is Y. You see this Y from the bottom to the location that we do the calculation.
Yeah, what's that location called?
Yes.
That location is called location that we do the calculation. We do the calculation. What kind of calculation that we are doing? We try to get P bar. P bar, right? If you want to get P bar, basically we have layer of liquid, right?
Yeah.
So layer 1, how much that is stay on top? Calculate pressure, hydrostatic head. Layer 2, how much that is stay on top? Layer 3, layer 4, layer 5. Add them together, divided by number of layer. Roughly, it is like that, right? If you want to know average pressure, we do it that way. Instead of add them together and divided by number of layer, we do the integration. So we have to calculate from bottom, change y a little bit, change y a little bit, change y a little bit until we cover every layer, right? So y is layer of interest. Okay, so total force due to hydrostatic pressure. How do we do the integration? So force is pressure times kind of area, right? That's force. So when we talk about when we talk about fluid element, okay, we want to know force in positive z pressed against the boundary, right? Okay, force from the fluid outside the control volume. So that force that we are talking about is a force not in the y direction but in the plus z direction. Okay. So if we have pressure, let's say we have this layer. So we want to know how much force that this layer acts on another fluid sit next to it. So it's the pressure multiplied by that area, right? And that area is B dy. Okay, B dy. dy is this thickness. B is this length. B dy is that small area. So B dy is the area that pressure acts upon to act on another fluid element. Okay? So pressure multiplied by area. And we do the summation of every pressure or every area, add them together, then we get total pressure or total force, right? So we calculate force on bottom layer, add with the force on the next one. Force is a vector. All of them are in the same direction, so we can add them together. So basically, we do the integration of pressure PdA. Basically, they do PdA and integrate it. Just that, from the bottom to top. Yes, Akin.
So each F will be the film height.
Yes.
So are we going to neglect inside the bubble, the gas, it will also have some pressure, right? Neglect that.
Do we neglect that? Yes. For Dr. Hubbard, yes. Should we neglect that? I think Tattobani didn't neglect it. And you will see another term in Tattobani. So in Dr. Hubbard, yes. There's no head due to gas or anything like that.
Shouldn't there be an integral for B as well?
Integral for pressure.
No, for B, because as you change up the H, and you move up from zeros, and you move up in Y direction,
Yes.
the B is also changing.
Do we account for that change? Yes, because that is that P, right? P change. This.
B.
Oh, yes, you have to account for the change of B. That's why we cannot move B outside the integral sign. B, small b, stay inside. We cannot take it out.
Yeah.
If it is a square or rectangular shape, we can take B out, right? But this, we cannot take B out. B stay inside.
Yeah, I'm saying general integral for it.
You see, what do we do with it? B change with y, right? B is a function of y. We cannot just take it out. So when we do the integration, we get total force. Okay? But we do this, all right? Let's go one line by line. I think it's maybe seem to be a lot. It's not. It is in your book. Okay? It is. Yeah, your book have this equation, right? How do you get equation 3.103 if you don't do this? Okay, that term that we are doing, this part is the force, right? So force is the same as that one, P bar A H something, and we try to differentiate it with respect to dz. Okay, how do we take the derivative of integration? Sweta, how do we take the derivative of integration? d by dz of integration something something something. How do we do that? We use what rule?
Oh, you,
We use some kind of rule, right? What rule? What rule?
I don't know what.
You don't remember what it's called. You don't remember what it's called. Who? Maya, do you remember what rule? What rule do we use? Yeah, Leibniz rule. Yes, yes, very good. We use Leibniz rule to do the differentiation or with the integration sign. We use Leibniz rule. So from Leibniz rule, d by dt of a as a function of t, integration from a to b of f, which is function of x and t dt, when we take the differentiate. So first step, do the partial derivative, okay, plus dip of upper boundary and use that function but put b directly in, okay, minus differentiate of the bottom derivative, bottom limit, and put that limit in. So the derivation of this is like chain rule or something. Okay.
Should it be dx
Which one? Over here?
first?
Over here? dx?
Because if it's dt, you can just get it out.
Yeah, something may be wrong. Should it be dx?
Yes.
So imagine that it is
I
dt.
think I copy it right. Copy right. I copy it correctly. So when I copy it from the book, it looked like this. I will check, but I think I copied it correctly.
Because if it is dt, if you want to get the derivative of that, it's going to just come out f, x, and t, right?
Take the derivative of which one? d by dt?
Yes.
Okay, I think I have explanation for you. Have you ever integrated something like
Let's
x
yes.
dx? You have done that, right?
Yes.
So the limit of integration, if this is from a to b, you can do that, right? But if a is also a function of x, or b is also a function of x, you can still do it, but it's a little bit complicated, right? So if your limit of integration is that function, we can still do it. To make sure that I did it right, let's check. How do you check it? How do you check if my slide is correct? Google it, let's Google it. Don't use Bing, okay?
Don't make it.
Leibniz rule. Did I do it right? It is x, it's not t. That one is x. That one is x, and that one is x. And okay, the rest is correct. So yes, this one is x. Have mistake. So this one is based on the chain rule. So when we finish the integration, we do step by step, okay? First step is do partial derivative. Thank you, Aya. First step we do partial derivative. Partial derivative is this term, not a problem, right? We just move this d inside and it becomes that, okay? And you can see that I don't have second term or third term because they are zero. Okay, dB by dt. So look at that. FB. So if I put this is my function f, right? That is my function f. If I substitute the upper integration limit in for y, it will become h minus h, which is 0, right? So this term is gone. So dA by dt, what is A? A is 0, which is constant. Derivative of 0 with respect to z is 0. So this term is 0, so makes the second term, the third term to be 0. So these two, they are gone.
So, okay.
Yeah, I'm waiting.
You didn't change anything.
Put,
Nothing changed.
oh, there's a change. You see this? We change from outside to inside.
Oh,
Okay, and Leibniz rule is the reason that we can do that change.
then what did you say after?
So f, you see this f, which is this whole thing. When we put the upper limit in, we put hf in place of y. hf minus hf is 0. So this makes this term 0. And dA, A is 0. D0 by dz is 0. So that term is gone.
Okay.
Derivative of lower limit, which is 0. Dip 0 is 0. So we can change total derivative, put it in, and it become partial derivative. And now you don't need to wonder, what's that? Oh, Leibniz rule. Where's the derivation of that? I bought the book, it shows the derivation is pretty lengthy, but it's correct. Okay. And after we put it in, we do partial derivative, right? Which one is a function of z? Z is distant, backward, right? Rho is not, okay? G is not, cosine theta is not. What about b? Is b a function of, direct function of height, which is y? Or yes, right? But it's not a function of z. So it's independent from z. So we can take b out. Okay. What about y? Y is like coordinate x and y, coordinate y and z. They are orthogonal. They're independent from each other, right? So we don't have anything to do with dy. And this term, we can we take it outside the integration sign yet? Okay, let's begin this. So the only term that is a function of z is hf, right? Film height is a function of z. Correct? Film height, change with distance. Okay. So dhf by dz, is that a function of y? What is dhf by dz? Who want to answer? You want to find? Okay. Akin, what is dhf by dz? Is it positive or negative? Okay, first of all. HF is film height. HF is film height, which is that, right? dhf by dz is a slope. Slope is like moving downward when we move with z, so it's negative. So dhf by dz is a slope of the film shape, right? Slope of the film shape. It's not a function of y when we do the integration from y, because the film height is not within y to begin with. So we can take it outside the integration. So we take this term out, right? And integration of b dy from 0 to hf is, oh, who want to answer? Vega. What's that? Integration of 0 to hf of b dy. What's that? What's that? Say it.
The area.
Yes, the area, right? b dy, when integrate it, we get this area, film area, right? Film area is AP multiplied by HLTB, which is that one. Okay. So now we know that d by dz terms, d by dz of that hydrostatic head term equal to rho g cosine theta something something something. Okay, and we put it here, equation 3.103. Earlier on we do summation of f equal to mh, yes? Is this not the same as in the book or?
No, you have to check minus y. I can just take out the check. It doesn't make sense.
This hf minus y?
Yeah, you just took out only the check. Can you do that?
I haven't tried. Can you try and tell me, is that work?
That's what you did.
That's what I did, yes. Is that what I did, yeah? What is your, how do you take the derivative or something? This, take on this become dHf by dz, right? So, we take the derivative of that, yeah, and the rest stay or what? If you can do it other way, there could be several ways of doing it. I know this way. If you know other way, please tell me. I will update the slide. Try it and tell me, okay? Try it soon, try it quickly. Before lunch, don't have lunch. Okay, yes.
So the HLTV is going to be the average pull-up, right?
HLTV is HLTV at that location. In this case, it's hold up at that location. Okay. And we go back from our starting equation, Vf equal to x divided by something. Okay. You see this term? This term is a term on the right hand side, left hand side, right? VDM. VDM is this part. D of v square a h. Take the derivative. We get this term. Okay. Take the derivative. Can you take the derivative? What I'm doing here, okay. Substitute x inside. Okay. This term is Vf, right? I put it there. Okay. I take the derivative. X squared is here. X is not function of z. I take it out. So this term come out. Right? Rho come out. AP come out. So I have d by dz of 1 over h LTB. 1 over h LTB is h LTB prime divided by h LTB squared. Make sense? Not make sense? Okay, let me change the battery.
That makes sense.
Change the battery.
Change the battery.